4 bits. You know what is XS3. You know what is XS3. So BCD representation can be done only for numbers 0 to 9. Only for numbers 0 to 9. Because only 4 locations are there. 4 locations are there. Okay. 0 to 9 only you have to represent using BCD. XS3. XS3 means BCD plus 3. Any value in BCD representation, normal BCD representation, any value in normal BCD representation, you add plus 3, that becomes XS3. Okay, this is XS3 and it doesn't have any position values. In the previous slide, you can see XS3 comes under non-weighted codes. XS3 comes under non-weighted codes. It doesn't have any position values. It depends on BCD. Whatever BCD is there, you will add plus 3, that will become XS3. Okay, so if you have a number 43, each digit, if this is a decimal value 43, each digit should be represented with 4 bits, 0100 0011. This is the BCD equivalent. This is the BCD equivalent. Every digit in decimal should be represented using 4 bits. Okay, so this is about the different types of codes. Next, I will go with ones complement, twos complement. For binary number system, how to calculate ones complement and twos complement. Okay, always this representations will be used for negative numbers. For representing negative numbers only, we go for ones complement and twos complement. For representing only negative numbers, we go for ones complement and twos complement. Okay, next slide, let me check. So we'll finish this and go to the next slide. For example, if I have a value 43, which is decimal number, 43, which is decimal number, what is the equivalent binary representation? What is the equivalent binary representation? If you divide with 2, it becomes 2, 1, 1, and then 2 means 10, 1, again 2 means 5, 0, and 2 means 2, 1, again 2 means 1, 0. So 1, you have to go bottom up approach, and 1, 0, 1, 0, 1, 1. 1, 0, 1, 0, 1, 1 is the value for 43. Okay, binary value for 43. And as it is positive number, you need not all the ones complement, twos complement will appear same. Okay, all the ones complement, twos complement. I will come back to this little later. I will go to next slide. I will come back to this. Range of representation. Range of representation. We have two types of numbers: signed representation and unsigned representation. Okay. For example, numbers can be numbers representation. Any numbers representation, it can be done in two different forms. One is unsigned representation. Second one, signed representation. Negative numbers compulsory, we should go for signed representation. Okay. And in signed representation, we have three different ways. First one, signed magnitude form. Second representation is ones complement representation. Next one is twos complement representation. Okay. And if you see, the maximum numbers you can represent in unsigned is 0 to 2 power n minus 1. 0 to 2 power n minus 1. In signed magnitude form, it is minus 2 power n minus 1 to plus 2 power n minus 1 minus 1. The same range. Okay, this is the range of representation that can be done. The red color what I am writing is a range of representation that can be done in signed magnitude form. Twos complement form also same. Minus 2 power n minus 1 to plus 2 power n minus 1 minus 1. Okay, but in one's complement representation, negative and positive are same. 2 power n minus 1 minus 1 negative side to 2 power n minus 1 minus 1 on the positive side. I will tell you what is the meaning of what I am going with now. If I take 3-bit representation, okay, we all know that if I take 3 bits, I have 3 bits representation I want to do. 3 bits only allowed. Then the maximum numbers I can represent is 0 to 2 power n minus 1. 2 power n minus 1. So this I will write in this manner. Two power n minus 1, and here I will put square bracket. In 3 bits, using 3 bits, I can only represent 2 power 3 minus 1 means 0 to 7. Okay, so numbers that I can represent is 0 to 7. 0 to 7. Okay, these are the numbers I can represent using 3 bits. These are the numbers I can represent using 3 bits. But if you see sign magnitude form, I have only 3 bits to use. I can represent minus 2 power 3 minus 1 means minus 4 to plus 3. Minus 4 to plus 3. These are the numbers I can represent using 3 bit. Okay. Minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3. Only these numbers I can represent. And in 2's complement form also, it is minus 4 to plus 3 I can represent. Minus 4 to plus 3 I can represent using 3 bits. Okay. And now coming to 1's complement representation, it is minus 3 to plus 3. Minus 3 to plus 3 I can represent in 1's complement. These are the numbers I can represent in 1's complement. Okay. So this is about range of representation. For example, if you take some other, if you take 6 bits, if you have 6 bits, you are allowed to represent, or you are allowed to write a number using 6 bits. Okay, if you have 6 bits, then the numbers differ. 0 to 2 power 6, 64. 64 minus 1 is 63. 0 to 63 are the numbers in unsigned. If you are not putting any plus minus, unsigned means no sign. Okay, all are positive only. So 0 to 63 is the representation you can do using 6 bits. But in sign magnitude form, it will be minus 32 to plus 31. Okay, using sign magnitude form, it will be minus 32 to plus 31. In 2's complement also, it will be minus 32 to plus 31. In 1's complement, it will be minus 31 to plus 31 only we can represent. Okay. Now, if I go to the next slide, this is the range of representation, and what are the numbers. If you have number of bits, okay, what are the numbers you can represent. Now coming to the binary number system. For 43, we had the equivalent binary. Okay. Now, this is unsigned representation. Because it is 43. Okay, because it is 43. How many bits are required for representing 43? Plus 43, how many bits are required? You can check. 6 bits, maximum 6 bits are required. Okay, to represent plus 43. If you take minus 43, this is unsigned representation. First one, what I have done, it is unsigned representation.
Ma'am?
Yes.
Why we have written the base 10 here near 43, ma'am?
Base 10 means this is decimal. I am taking a decimal number 10. Okay, base 10 means I have taken a decimal number 10. I am converting it to a binary representation. I am converting it to a binary number. So what I have discussed in the next slide, this numbers 0 to 7 is decimal numbers. You can represent decimal number 0 to 7. Okay, using 3 bits. And here 0 to 63 I have written in black color, 0 to 63. Those are decimal numbers that can be represented using 6 bits binary. Okay, number of bits required for representation in binary, and what are the numbers we are talking that in decimal. Okay, and this is the range, general formula, 0 to 2 power n minus 1. That is the general formula. If you see minus 43, this is negative number, so we have to go for signed representation. In signed, again, for negative numbers you have 3 different types of representation you can do. One is signed magnitude representation, second one ones complement representation, and then two's complement representation. For negative numbers, compulsory ones complement, two's complement are used for negative number representation. Okay, so as it is binary, you see here binary means the radix is 2, base value equal to 2. Binary means radix or base value equal to 2. So for binary, what are possible? One's complement is possible and two's complement is possible. One's complement possible and two's complement is possible. Okay. So similarly, if you go with other number system, if you go with decimal, octal, hexadecimal number system, we know that decimal means base is 10. Decimal means base is 10. So for all decimal numbers, we can calculate 9's complement and 10's complement. 9's complement and 10's complement possible for decimal numbers. We know that octal means base is 8. Octal means base is 8. So for octal numbers, we can calculate 7's complement and 8's complement. 7's complement and 8's complement. Okay. And coming to hexadecimal. Hexadecimal means we know that base is 16. And therefore, for hexadecimal number system, we can calculate 15's complement and 16's complement. Okay. So presently in our theory, we study only 1's complement, 2's complement. These are other complements present. Okay. So now I will go with a problem. I will go with a small problem. So to make the topic clear, calculate 9's complement for 102.7. 102. Calculate 9's complement for 102.7 base 10. Okay. Base 10 means this is decimal number. Okay. Given is decimal number and 9's complement is possible. 9's complement, 10's complement is possible for decimal number. How to calculate 9's complement? You have to take the number what is present, what is given, number what is given. You subtract every digit from 9. The answer is 9's complement. Okay. 2, 7, 9, 8. This is the 9's complement for given number. Okay. So this is the 9's complement for given number. If you want to calculate 10's complement, add plus 1. Add plus 1 to the LSB. Okay. Add plus 1 to the LSB. That will give 10's complement. That is general. For example, if I give you another question, calculate 9's complement for 102.7 base 6. As base is 6, okay, possible is 5 complement and 6 complement only. Base 6 means 5 complement and 6 complement only possible. So 9's complement cannot be calculated. Okay. So based on the radix, different types of complements exist. This is the conclusion from this theory. Okay. From